simple systems to study hydrodynamics in. And so the work was done in collaboration with Sanbu, who is a PhD student of Kerr, Juan, who was him, and Benjamin, who was here. So the kind of system that we study are brickwork circuits. So in particular, it's classical one-dimensional deterministic brickwork circuits. So what this means is you have a lattice, and each side of the lattice you have some local state AX. It can just be a number between 0 and d minus 1. So for most of the talk, d will be free, so on each lattice side there can either be a 0, a 1, or 2. So you have your initial state down here with all of these numbers. And now what you do in time is you pick out two sides, and then you apply like some local update rule to them that somehow takes these two numbers and outputs you two different numbers, two new numbers. And like in this kind of notation, you write it like this. Kind of here the states that you start with, here are the states that come out, and then if you apply the circuit here, it means that up here will be the new numbers. Right, and now I apply these ones I applied on all like neighboring sides. And then in the next time step, what I'm going to do is I'm going to do the same thing but shift everything by one side. And this way I get like some non-trivial evolution coupling all the sides eventually. And then I just decide to do this for like a couple of times. And eventually I measure some observable. In this case I measure some two-side observable A here. And you just write it like this. And then on all the other sides you put like this flat state here, which is just one all the time, so it's just like it discards all the information on that side. Is that clear? Like it's a very simple dynamical system. So like these kind of systems, they can be thought of like time discrete versions of like many body systems. They exist in classical systems, and they're also called like automata. And in quantum, they are called quantum circuits, which are very important for quantum computing and so on. So the nice thing about circuits is that they are very efficient to simulate, like let's say on a computer, because you don't need to take like the time discretization to 0. Right? But still, of course, if you want to do like some large-scale simulation, large space, large time, that's very demanding, right? So there exist some techniques for chaotic circuits that don't have any conserved quantities. For instance, these random circuits where you average over the randomness, or some solvable circuits, for instance, these two unitary ones. But kind of for like circuits with like some conserved quantities, like techniques are missing. And what we did is we developed some tools to study like conserved quantities in these circuits. And these tools will be generally applicable to like any kind of circuit structure, like classical, quantum, also high dimensional. Here we only do the one-dimensional classical case. But then the thing we are excited about is that there are some analytic results in some special models. So and like here's the picture, right? So I like in this model here that there's some update rules, right? Like 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. 0, 2 goes to 1, 0, and so on. And then you kind of can let some simulations run, and yeah, I mean, you see something, or not much, like something happening. But now what I'm telling you in this model, there's a conserved quantity. So, and then of course, if we make the system very large, so here we go to system size 3 million, you put some initial state there. Then if we like cross grain and get a distribution of the charge, we can actually predict its evolution by hydrodynamics. Right, that's like the idea. Okay, so I guess we all know the hydrodynamic approximation, right? It's some kind of generalization of the Euler equations of fluid dynamics. And the idea is if you have a general system with some charges that are sum of local terms, then we go into this Euler scaling limit where we look at large times, large spatial scales, and also the total charge is going to infinity. So we study finite density and finite velocity state. Then because of the local interaction, we should get like local thermalization to some local temperatures here. But then these temperatures will vary across the system. So there will be a slow function of the system size. And yes, so when you assume like this kind of Gibbs states that's like spatially varying, in the end you can come up with these Euler hydrodynamic equations, which then couples the expectation value for the charge with the expectation value of the current. Okay. This is really powerful, but the problem is this kind of procedure cannot be carried out in practice, and therefore hydrodynamics remains an effective description, which is of course very, very useful, as we all know, but in particular, like how do we actually get to hydrodynamics is not well understood. And like sort of the first problem that you have in there is, okay, like here on the last slide, we needed to compute these thermal expectation values, but we don't know how to do it. Right? And so the problem for this is if you have a time continuous system, let's say you have some spin chain, the Hamiltonian is always conserved. And the Hamiltonian also has to couple two or more sides. Right? Otherwise it's a bit trivial. So, and then if you have something like this, then exponential of minus beta h, we don't know how to compute, like in like, let's say, a quantum spin chain or so. So there are some exceptions to this. So there are some classical model of finite range interaction. For instance, think about the Ising chain. There's this transfer matrix method that allows you to compute them. Models, which leads to this generalized hydrodynamics. And kind of now what we want to add to this is like these circuits, where we can also do things. So, and the reason why circuits are nice is for a very simple reason. The circuits break time translation invariant, so there is no conserved Hamiltonian. Which means the generic circuit will have no conserved quantity. But now let's say the circuit additionally has a charge which is just the sum of single side quantities, for instance like some particle number, total magnetization or something like this. Then the Gibbs states, I mean you can like, they just factorize. So there's basically, I don't know, trivial to compute the Gibbs states, right? And these are precisely these circuits for which we can obtain analytical predictions. So now the important task is we need to find all the conserved quantities for a given circuit. And this is a very hard task. And it should also be a very hard task in like usual systems. Like if I write it on a spin chain, it should be a very hard task. But the thing is, we usually go about this and we look at the system and be like, okay, there's like energy is conserved, particle number is conserved, maybe some momentum is conserved, I don't know. And then we just know what the correct conserved quantities are. Right? But there could be more that are just accidentally conserved and we don't know. Problem is here, we don't have any canonical conserved quantities, so we really need to go about understanding what are the conditions for conserved quantities. So, and this is going to be the first thing I'm going to tell you is like how to find conserved quantities in these circuits. And then the next step will be we will find some of them, and then we want to check that there are no more conserved quantities. And then once we have these two things, we can then really write down the Euler hydrodynamic equations. And then we can also, as the last step, I will tell you a bit about nonlinear fluctuating hydrodynamics. Okay, so the first thing to notice is that circuits, they are translation invariant by two sides. So if I want to write down a conserved quantity, it can be different on the even and on the odd sides. So it's like a sum of something on even and the odd sides. And now the condition that we find is the following. So you write it down in this language like this, but what it means is you apply a time step, and now you measure your conserved quantities by summing the odd side and the even side. And this is the same thing as measuring them the time step before, but on opposite sides. And there are some prefactors here. So if these two prefactors are 1 or -1, then you get a usual conserved quantity that's conserved after two time steps, just like the canonical thing that you would expect maybe. But these lambda and these mu's can be, in general, they can be arbitrary units of unity. In this case, there would be conserved quantities that are conserved after, let's say, some 2n time steps. And like for hydrodynamics, we need to take all of these into account. Okay. So we have a generalization of this formula I showed on the last slide for like conserved quantities with like larger densities. So on the computer, if you give me a circuit, we can check like for the existence of conserved quantities up to like nine sides, which is pretty big, I guess. So then for local dimension d equal 2, so on each side there can either be 0 or 1, and we found that there are either no conserved quantities or apparently infinitely many. Therefore, we studied d equal 3, so on each side there can be 0 or 1 or 2, and then in total you have some 300,000 gates, but like checking these conserved quantities is quick, so we just did a search over all of them, and we identified some 2,000 gates that only have single side conserved quantities.
Sorry, question. For d equals 2, that naively counts just particles hopping with conserved particle number? Is that not a...
Yeah, yes. It's like infinitely many conserved. Like if you just do like a swap gate, like every particle just moves like the position of the particle swap.
Higher gates to make it not free. Yeah,
and so in this case it would be integrable. Yes. So, but now we have all of these gates, and now
but actually on that point, I mean, sorry, is the circuit completely deterministic?
Yes.
Ah, okay.
It is.
Then I understand. Okay.
And it's also invertible. That's also invertible. So now we have all of these gates, but the problem is, there could be bigger conserved quantities, and we cannot find with the numeric algorithm. And also, there could be these like quasi-local conserved quantities that we also now contribute to hydrodynamics, like conserved quantities that are not sum of like I don't know, like 5-side densities, but densities that kind of are everywhere in space but decay exponentially fast, for instance. And this kind of is related to like a more general question, like if you have a system of size L, let's say a quantum spin chain, right, something, then it always has d to the L conserved quantities, namely any eigenstate to the time evolution operator, but like, I mean, those are obviously not local, most of them are not local, and the question is which one to pick for hydrodynamics. And okay, but now there's some understanding, some theory for this, but kind of our idea was like, let's just circumvent any of this theory construction, let's just like be intuitive, and the idea is like, all the conserved quantities that should be relevant for hydrodynamics are all the conserved quantities I can relax to, like kind of, I can formalize to, right? Like, so kind of the number of conserved quantities should be the number of Gibbs states that I have in my system. And so, but this is very easy to check, so you just start with some random initial state. You evolve it for some time, it should like relax to like one of these thermal states, and then the only thing you need to do is you need to somehow count what is the dimension of this manifold. So if you have one conserved quantity, they will all fall onto like some one-dimensional subspace. If you have two conserved quantities, they will put on 2, and so on. So, and this is something that we can carry out in practice. So here we just like start the evolution from some random initial state, and then in the end we measure 2 observables, some generic observables, and we find that the points that we observe, they all lie on some one-dimensional submanifold, and it's also agrees with the thermal expectation value. So this really shows that in this gate you have one conserved quantity which is relevant for hydro. And then, so kind of we have, for instance, this other gate here where it's like a 2-dimensional surface, and yeah, I mean that's why you then know that this circuit has 2 conserved quantities which are relevant for hydro.
Sorry, what are you plotting here? I'm a bit confused.
So you just choose like some A, B, and C are some generic observables. You choose like, you fix it at the beginning, but it's just something generic. It's 4-side conserved quantities. And then you start the evolution from a random initial state. And like each of these blue crosses here is like one result of like one of the simulations.
For a long time.
For a long time, yes, for a long time. So they all fall onto the submanifold, and that's why it's like a 2-dimensional. It's a 2-dimensional manifold. Yes.
So observable should just depend on 2 chemical potentials, essentially. And so that's why any observable will fall into a 2-dimensional manifold of some sort.
Okay, so that's great. Now we have established that we found all of these conserved quantities. And this is the moment when we can actually do like Euler-Hydro. And so, and the thing now is we can really compute the hydrodynamic equations. Like we don't have to guess them, we can just compute them, right? And so, like for usual conserved quantities, where like that are conserved after 2 time steps, the explicit formulas are here. So the charge is the sum of the contribution from the even and the odd side, and the current is the difference between what's on the even and on the odd side. And for instance, for one of the models that I showed you before, we can just like compute this explicitly, and then we find a hydrodynamic equation that looks like this. And this equation is equivalent to Berger's equation, which is, it's like the simplest equation of like hydrodynamics that you can maybe imagine. And Berger's equation is not possible to achieve in time-continuous systems. So it's actually quite nice that we can obtain like much simpler equations here. And also what's interesting about this equation is that it has shocks. And I mean, not in like a Hamiltonian system without noise, closed Hamiltonian system without noise. Like there are some theorems for this that prevent this from happening.
What do you mean by equivalent? I mean, it's just identical or similar, or what do you mean?
You can do a rescaling. So if you do like a function q to f of q, and you choose the f of q in a particular way, then you just obtain Berger's equation.
Oh, I see.
It's like it's a real label.
It's a real mapping of the 2 equations.
Yeah, I mean, so the only difference to Berger's equation is that this conserved quantity is bounded between -1 and 1, I think. And Berger's equation, of course, goes like you have no bound on the conserved quantity. That's like the only difference, but it's somehow, it's a marginal difference. And now one of the nice things about these circuits is also that we can very easily do calculations. So we can actually track these things. So what you see here is we initialize the system. It's a periodic box with like this gray curve here. It's a smooth curve, and then we evolve. Then we just let the evolution run. And what you see is like it's smooth, and eventually it forms these discontinuities, which are called shock. Right, and what you can see here, maybe not see well. So there's always a solid line, and then there's a dashed line. So the solid line is the microscopic simulations, and the dashed line is the hydrodynamic prediction. And you can only see one line. So it matches quite well. And so actually when I gave this picture to Juan, one of the collaborators, he was like, it's a very nice picture, but can you please change the line width such that the line width of each curve is the same? But so the line widths here are not, it's not some line width I chose, this is like the numerical error. It's very, like it's tiny, like.
Shock formation you could have also in continuous systems, right?
Yeah, of course. It's not. But getting Berger's equation is.
Yeah.
When do you have to average over 10 to the what is this?
I will explain in the next slide. But like, so hydrodynamics is like you take like the expectation value of like some of the conserved quantity. So this is average. Like I draw my initial state is given by like locally thermal distribution that follows this kind of curve here. But then, of course, I can draw many samples from this, and they will slightly look different. And evolve and then average over them. Yes.
But then there should be some noise, no?
I mean, the noise is like this. Like the line width is the noise. So this is the plot I showed in the beginning, and when you look at this plot, like there's much more noise than in the last plot. So what happens here? In the last plot, I averaged over many samples, and here I just took a single sample from it, and I evolved it, and in the end I coarse-grained it, and this is the evolution. So, and it also follows hydrodynamics. So what you learn from this is hydrodynamics is self-averaging, right? Which is something that you also might expect, but here you can like very simply check it. Like. study the entropy in the system, and so hydrodynamics, the entropy is like, in all hydrodynamics the entropy is constant, but then you have the shock, and the shock can produce entropy, and that's actually something that we can just check. So it's constant here, and then it starts to increase, and eventually it reaches the maximum possible value, which signals like permanentization.
Once you get shocks, I guess you want to go beyond Euler hydrodynamics too.
Like in principle, yes, but like the thing is, you can like, so if I do like numerics which are like, this is a very big system, like I don't know, 10 to the 5 I think, or something like this. But if I do like, let's say 1,000, then these things are like smoothened by, like in this case it's super diffuse, but it has some smoothing there. But the thing is, when you really make a system very big, then in the end you can study this just by imposing some boundary condition for how the shock moves, and you can fix this by like imposing that the entropy increase has to be positive. So in some sense, what we're doing here is we are also kind of checking that the recipe to deal with shocks is correct. Right? There's some freedom to choose what to do with the shocks, and this recipe is the correct one.
But how do you make what's the theoretical cure for the entropy increase? How do you obtain?
So you just take this curve here, and then you have the entropy as a function of charge. Like you have, in like a Gibbs state, you have the entropy, which you can express as entropy as a function of charge. And then you write this, I mean, you compute this, and then you integrate over all of space, and then this gives you total entropy.
It's total hydrodynamic entropy.
Yeah, but you plug inside the charge of the simulation, not the hydrodynamic charge, right?
The charge of the microscopic simulations. Yeah. And this is also, I mean, you can see that the numerics curve is slightly above the, like the microscopic numerics slightly above the theory, and this is because of the super diffusive broadening, which increases entropy faster.
But what is theory here?
The theory is hydrodynamics.
In Euler hydrodynamics, there is no entropy increase.
I mean, once you have, that's done here, but once you have the shock, then you have the entropy increase.
No, but you have to put diffusion.
No, you just calculate total atomic entropy. It increases, on both sides of the shock. It's going to change, right? The shock itself is a source of entropy.
And you kind of, in some sense, you make a guess how does the shock evolve, which is a very natural guess that it increases entropy. And this, I mean, it's a non-trivial guess, let's say, but here we check that the guess is kind of correct. Okay. So before we studied one-point functions out of equilibrium, and now we can also apply hydrodynamics to like fluctuations around an equilibrium state, so correlation function in an equilibrium state. And for this, there's like this famous theory of nonlinear hydrodynamics by Herbert Spohn, which means you expand your current up to second order in the perturbation, you add some diffusion and some noise, and then you realize this can be mapped to a KPZ equation, and this gives you two-thirds super diffusion, so the correlation function is like this two-thirds scaling, and there's like some super diffusion constant here, let's say, which only depends on the second derivative of the current. And so this is something that we can also compute. And so we did some numerical simulations, and the full half maximum of these correlation functions just scales perfectly super diffusive. We can check that like the shape, like when you rescale the shape, that it collapses to like the function that you expect. And also this, we can extract the super diffusion constant numerically, and we can compare it to like the theoretical prediction, and it fits perfectly. I mean, just as you would expect probably. So then we also have some models where you have like some special point in which the second derivative of the current goes to 0. So the super diffusion constant goes to 0. So this is here at this point. And there, what we find is that it's diffusive at this point. So only at a special point it grows diffusively. Yes. So to summarize, like what we did is we established hydrodynamics in these non-integrable classical circuits. For this we developed some new tools, which are techniques to find small conserved quantities, and then a technique to find the number of conserved quantities. And combining those, we can be sure that we find all conserved quantities. And then we are able to analytically predict the hydrodynamic equations in models which have only single-site conserved quantities. So we can find the Euler equations, we can check for shocks and entropy increase. We find agreement with nonlinear fluctuating hydrodynamics, and all of this is an excellent agreement with numerical simulations. And like, I mean, I guess everybody here has their favorite platform for hydrodynamics, but like, at least from everything that I've seen so far, like, this is really like, it's really simple to obtain the hydrodynamic equations, and also really simple to do numerical simulations. So, I know, in my opinion, it's like the simplest platform to do this. So in these circuits, there are even more interesting things that come up. So one thing that we found is that there's some kind of circuits that have some FPUT-like phenomenology. So for like short times, they somehow look integrable, but then on long time scales, they then realize that they are not, and then you have a very slow transition to hydrodynamic behavior. Then, like a week after we published our results, another preprint appeared on arXiv by a group in Ljubljana, and they didn't do hydrodynamics, but they looked at the same circuits, and their paper is basically a classification of all possible behavior you can have in these circuits. So if you're interested in them, it's worth looking at. So they classify them by symmetries, fluctuation, conserved quantities, and mean return time. They have some alternative method to identify the conserved quantities, which allows them to also identify circuits with quasi-local conserved quantities. And they actually have some which have like 1, 2, and also many of these quasi-local conserved quantities. And they also find the KP-set scaling. And then, so talk by Takato that we had yesterday, in like his models had like some deterministic point, and this deterministic point is actually also in the class of models that we study here. Yes, so as an outlook, like all of these tools are straightforward to extend to like quantum systems, high-dimension systems, other circuit topologies. So what we are currently working on is we try to identify interesting quantum gates and high-dimensional gates. So in one-dimensional systems, classical system, I told you there are these other time-continuous systems where you can do hydrodynamics. But in these systems, it would be like the first non-integral models where you can predict the hydrodynamics. Then it would be interesting to study these quasi-local charges, understand these features of these staggered charges, try to extend the results to also stochastic circuits. And then, I mean, in general, I know, like for now we are able to predict the hydrodynamic equations, but we cannot like check it from the microscopics. So it would be interesting to see whether in these circuits you can actually understand where it's coming from microscopically. And one thing we're also working on is trying to combine this with other circuit techniques, for instance, solvability. And the solvability might allow to obtain exact microscopic predictions that you can compare to the hydrodynamics. Okay, and with this, thank you very much.
Since you mentioned the shocks, I mean, what is usually expected is that the shock is sort of sharp on the scale of a few lattice-sites, but then the location of the shock is fluctuating from sample to sample. And I just wonder whether you ever tested this. I mean, I guess maybe the easiest way to test it would be to start with a sort of step initial condition or with a domain ball. Basically prepare the shock at time t equals 0 already and see whether you can sort of see these fluctuations.
You mean the fluctuation in the position of the shock?
Yeah, it's just it's really sharp on the lattice scale, and then it's sort of it fluctuates from sample to sample.
I mean, our shock is not sharp on the lattice scale.
Yeah, because but you generated it. Well,
I mean, we have the KP set super diffusion.
No, I mean, because your shock should be very sharp. Yeah, I mean, your shock is sharp. I mean, KPC is something different. KPC is just a correlation, right? I mean, but not.
Oh, but Like if
Yeah, this
you do these simulations here and I do like smaller system size, then you really see like that there's some broadening here.
yeah, that's fine. But what I'm saying is, I mean, this jump, you know, should be confined to a few lattice sites only. It's
I don't think so.
not something which is broad.
I mean, okay, maybe I have to think about it. I don't think. I think it's like it looks small on the microscopic scale, but microscopically it's bigger.
No, that's the whole point.
Okay.
Microscopically, it should be sharp on the scale of the lattice, right?
Okay, yeah. No, I mean, interesting. Like, I can.
I see what you're saying. I mean, sort of, you know, you might think that it's sort of smeared out a little bit on the microscopic scale, but this comes from averaging. I mean, if you do a fixed realization, it should be sharp on a scale of a few sites. I'm not saying it has to be, you know, it's just sort of what one finds in other systems, and it would be interesting to see that also here.
No, definitely. I mean, we could check this quite easily, I guess.
So if it expands like super diffusively, they wouldn't produce linearity entropy. It would be sublinearity.
Final quick question.
So maybe you mentioned, can you go to the next slide? So this thing, so is it? It's not sharp, right? So is this like smooth at the entropy growth there? Can you say something about? Yeah. So
I mean, like, so if you have a finite system size, then like this is smoothened out because you have the super diffusive broadening, and then this just smoothens things out. If you really go to like the L to infinity limit, then this becomes.
Are the corrections exponential or?
Corrections what?
Exponential in the number of, I mean, on the size or? Corrections to the sharp transition.
I don't think like it should be somehow have to do with the 2/3 of the KP set, like, but I don't know precisely what the. But I don't think it's exponential. It should be somehow though.
And here L is not system size, right? This is just the.
I mean, L is system size in this case. This is and it's a periodic box with just L size. I think in here is L is 10 to the 5.
Why do you have to take such big size?
I mean, because otherwise, like you have the super diffusive broadening here, and I mean, like I did it so big so that the super diffusive broadening. Like, it increases better, like if you make it bigger.
Okay, maybe in the interest of time, let's thank Friedrich again.